Welcome back, everybody. Last week we talked about chapter 6 regarding the dimensioning system, dimension components, laying out dimension, and steps in dimensioning. And now we're going to continue on to finish up the chapter 6 about specific dimensioning techniques, summary of dimensioning rules, some of the notation, and we want to learn the rules for applying some notes on drawings. And then we're going to summarize the entire chapter, and then we're going to finish up this chapter 6 with some review question. So uh, to continue on from last Thursday, we talked about the finish mark. As you can see, the finish mark, we have a transitional system here, and then we have a general system here. And the new system is going to be a short little check mark here with a 60 degrees, and the longest mark here is about 0.36 inches, and the shorter one is about 0.18 inches. And the transitional system and the general system has been replaced by the new system. However, engineers should be familiar with all of these three systems so that they are prepared to interpret finish mark applied to drawing produced in years past. So as you can see, the finish marks, meaning the anytime when you have a rough surface and you want to smooth it out, that's how you finish it up. And the from this example here, you can see from the highest point to the lowest point, that's a total measure micro inches. If this micro inches the total distance between here, the highest to the lowest, the elevation is 1 to 5. To convert that into micro inches, you're going to have to use the conversion factor, which is 1 micro inch equal to 0.00001 inch, and simply multiply that conversion factor with 1 to 5. That's give you 0.000125 micro inches. So what is that finished surface? Finished surface, when you have the original rough surface and you want to tell the manufacturer that you want to smooth it out, and by pointing to the surface that you want to finish it. So the extra material provided to produce the desired surface finish. So this is going to be original. Now you're going to have to reduce it in order to make it smooth. Again, the finished surface can be show a check mark, and this check mark here, they show all these surfaces must be finished, must be really smooth. So the proper method for applying micro inches callout to finish mark. Notice that micro inches callout are not used with the traditional finish mark system. Traditionally, we don't use that, but then there's no number here. But if you look at the new system, that's what we have to show the how fine-tuned do you want that finish mark to be. So for 63, and that's 63. If you look up the table, this is a typical surface roughness height application. When the engineer call out 63 here, and you're gonna have to look up the 63, and the application for 63 is a good machine finished product under control condition using relatively high speed, and to fine tune that surface. So some of this they have a lot of different micro inches rating. The smaller the number, the finest the surface needs to be produced. Look at the rule for applying finish mark to drawing. Note that finish mark are to be repeated in every view where the surface in question appear as an H. So rule: finish mark must be repeated in every view where the surface appears as an edge, even a hidden surface. You like this for example, this surface hidden surface here. You're gonna have to show that um, to let the manufacturer know that this surface needs to be finished. So another good example about the XYZ coordinates. So the concept of the XYZ coordinates, in order to be able to fully understand the various dimensioning system, one must understand the concept of XYZ coordinates. This is particularly true in the case of tabular dimensioning. Note from this illustration that x coordinate move from an origin in a horizontal direction, y is going vertical direction, and z is moving from an origin in the direction indicated in the depth. And you can see some of the dimension we can use is, instead of calling that out, we make a tabular drawing. So you can see they're putting the dimension here as A, B, C, D, E, and then you're going to have to create a table and show, because this part here could be a different many part and could be a different dimension on each part. So what you're gonna have to do is to call out a table and specifically say that for this particular part, you need excuse me, you need to use A dimension is going to be 4.5 inches. B dimension you need 1.62, and C you need the diameter for C is 0.38. And it's only applied to this particular part. This is a good example about the tabular dimensioning, and you have a very complicated component and need to be manufactured, and because you have a few different parts, you have to specifically say for A1, A2, B1, B2, and so on, C1 to D3, they give you a different dimension. So for A1, so your diameter is 0.25 and the X is 0.3 inches. Your Y is 1.75 and your Z is either through or not through, and depend how deep you want that hole to be. This is all defined in a tabular dimension. So with that, look, I'm gonna end this video now and go on to video number 2 to continue on with tolerancing.